So we first start with a query model of computing. By the way, this is basically based on the IBM quantum tutorial, but I'm going to reinterpret this with my own understanding or relevance. So, sorry, I've lost my Apple Pen. Okay, I found it. From what I research or reading, so quantum computing doesn't solve all problems faster than classical computing. There are certain computational problems quantum computing can do faster than classical one. So the most important part is whether quantum computing can be faster than classical computing when working on similar problem. So there are certain type of problem where quantum computing can work much faster than classical computing. And this query model is one of them. First, the classical computing is basically if we have an input and then we put into some black box, and then we get the output. And this is basically and we call that a computational compute. This is what we call that the traditional or classical one. But there's another type of the computing, and that's called a query model. Let's change that to. And in this case, the input. Oh, by the way, in this case, we often have to provide all the input. So all the input into, if you leave out, it's not going to compute. So all input. Oh, that's not clear. In the classical one, we have to put all input there. If we don't input into computation process, we will not get the result. So there's another type for the query one, we actually just don't put all the information there. And this in fact, the input itself is considered as a so-called function. And then we do the computation. And we get the output. But the computation is actually done multiple rounds by the so-called queries. So we have to do that many times. This is the query model of computing. Now, because the input is only provide in this partially, we actually, I think the book actually defined this as the function. This can be abstractly called a mathematical function, or fx. We can just call that input, consider a mathematical function. So that's actually quite interesting, though. In the classical computing, like we use a calculator, if we put, say, log 100, we'll put 100 there, we calculate the 2. And for the query part, we actually, for the query model, instead of working on the numbers, we actually can query on the mathematical function itself. So this really is quite a different way of computing. So instead of computing on the actual number, we actually try to compute on the actual mathematical function here. So you can also clearly see if we're using a classical computing method to actually compute directly on the mathematical function will be quite challenging. So this is a quite an interesting way to pose a problem. So, okay, so the IBM tutorial actually then go over with the list of query problems. So what kind of input function or query problem can a query model computing work on? And there will be like all function parity problem, minimum problem, and the Deutsch algorithm is going to work on the parity problem. For example, the parity can be just even and odd, and very often the parity problem can be solved by the XOR operation. Here's also so for this toy quantum algorithm to work, and we are also going to simplify the problem into the so-called promise problem. Just for simplicity, this is basically almost like when we prove theorem, we give a lot of assumptions. That's the similar way. We're basically going to assume there are some conditions where the will be satisfied. If the input or the function doesn't satisfy the problem, we just do not even consider them. So just in a way, this is just to make us to explore how quantum computing work in principle. We can let go some of the complexities. So the book actually, not the book, the IBM tutorial actually then work on the example of some of the query, how to use circuit to address the query. One is the classical way to address using a classical gate to solve the parity problem, and that would be the AND gate, I believe. Let me try to, but I didn't write this on my notes, my apologies. So I have to go back and look at my notes again.
Yes, the The bar, like this is not.
This is not.
Upside down V is and.
This is and.
Yeah, and the V is or.
That's all. Okay. So, and that's the input. And this must be the XOR gate then. This must be the Boolean circuit for XOR. So, Hannah, you know how to explain this digital logic? Why this works are
So
XOR?
we have like the function. So if we look at that,
Mhm,
that means this is going to be like not F.
mhm. For this one, that's not F,
This
right?
is not F and going with the F below to the
Oh, maybe we should let instead of F, let's call this A. This is a B.
uh-huh. Yeah. So that's going to be not B going with this is not B going with the B.
Sorry.
Yeah, if we look at that, we have not
This is not A with a B, is it?
this is not A with B. And the top one is gonna be not yeah, A and not B.
I see.
And then
So
we all that together.
all that will be
A not B or A not yeah. The output at the end is gonna be A not B or not AB.
okay. Oh, sorry, I should have write that way.
Yeah, the B is without not.
Yeah. So
Yeah,
that's
they're opposite. Yes.
okay. Uh, okay. So this is the thank you, Hannah. This is the classical circuit for the XOR, but for the quantum, it actually uh, will be yeah. So this is actually apparently quantum computer is just given this, even though the outcome seem to, but since the top one doesn't do anything, we can just ignore it. That's mine. This basically nothing is being done on it, so we can ignore it. But the bottom one apparently apply the execute all on the strings, and this will the example to show this is uh, apparently Deutsch algorithm use this as an example to show the advantage of the quantum algorithm. Yeah. So does this make sense to everyone here? The idea is for the classical computing, we have the data input, all the data input coming computed. But for the query algorithm, instead of the query, what we are trying to figure out is actually the function itself. Uh, let's see. So, and then this is what the Deutsch algorithm going to operate on. So what is the Deutsch algorithm? So basically the input is the function. In this case, instead of number input uh, is a function f. It basically convert the some 0 and 1 to another 0 and 1. So and what the output is, whether this function is constant or balanced. Okay, this, oops, mistake. Now, what does constant or balance mean? The problem will be like simplified like this. If we have input is 0 and 1, oh, sorry, and we have the f1 of the function, it can be 0, 0. If we have an input 0 and 1, we have f2 function of the a, this can be 0 and 1. One zero. One one. So in this case, constant means these two are constant. And this, the last one is a constant because this is just a binary, and in the middle, the middle two, what we call balanced. So it's really a very toy situation just for the proof of concept. In this case, we have the input function so f4 and f1, we call that constant. f2 and f3, we call that a balanced. That's basically what this is. Even though we write it, I guess if we summarize, it's basically what this means. So the constant green, sorry. Constant is f1 or f4, and balanced will be f2 or f3. That's yeah, it's better than toss a coin, hopefully. So so the function convert input 0, 1 into 0, 0 will be 0, 0, 0, 1, 1, 0, 1, 1. But instead of work on the for outcome, we actually separate this for situation into two. The green one are the balance, are the constant, and the yellow one are the balanced. And this is actually not Deutsch algorithm. This is the problem that Deutsch algorithm trying to solve. So, am I making sense to you, everyone?
Yes.
Okay. All right. Let's. So the Deutsch algorithm, the gate. This is so simple. I'm going to just draw it. This is actually quite important. So the Deutsch algorithm work on two input qubit. So my understanding basically related to this two input. And it first apply Hadamard gate to each one of it. And then it give one quantum gate. That's basically is this Deutsch algorithm, the most important part. And then apply another Hadamard gate. And then just the measurement. And then look at the outcome. If the 0 f is constant. If it's 1, f is balanced. And the argument is if this is a classical, if we use classical computing method, we need to have at least 2 operations on this, 2 query operation on this. So either 0, 1, we need to have at least 2 query gate. But for the quantum computing, we can just using 1 query gate. So the argument is this is my understanding of why the Deutsch algorithm is important for classical computing. Classical query gate, sorry. So if we apply classical query gate, we need at least 2. For which is the quantum algorithm, we use only 1 query gate. So this is the basically what I understand is the importance of this Deutsch algorithm. It really doesn't solve any other problem, but it's just using this case to show quantum algorithm can be 1 step smaller than classical query gates. That's my understanding of this. Am I making sense, everyone?
You're making sense, but this thing is weird.
Okay. It's actually so Justin and Joshua, questions or comments on this part?
Not on this part, no.
No comments right now. I think I'm probably going to take some time afterwards to review the recording and maybe some of the IBM sections to help solidify it.
Okay, that's a good point. So I haven't gone to any detail how this is the implement. What I thought is when I approach this, I think I had trouble to understand the importance of the Deutsch algorithm. Actually, so just as you say, I thought I need to understand the procedure, the algorithm, how it's implemented. So I went directly to the Python Qiskit code. But the problem is after I go over the Qiskit code, all those, I still don't get that big picture of why it is important. That part I'm missing. So even though I go through all the code, trying to understand how it's working, it's still missing. I didn't appreciate why this is a big deal. So I'm trying to emphasize this part. This is what people think why Deutsch algorithm is important, because this is just my understanding why it is important. Yeah, that's my understanding. This in the Deutsch algorithm, we apply this 1 quantum query gate. My understanding is that if we're trying to apply the classical query gate, either N, X, or you need to from what I understand, you need at least 2 gates. Let's say that I'm not a mathematician or digital logic person, so I don't know how to prove that. But I guess you can try whether using the classical gate, what's the minimum number. You can try. I'm going to assume if it's a 0, 0, 0, 1. I can see because there are 4 possibilities. If you put, yeah, you probably need probably even need more than 2. Well, I guess if people say at least 2, there must be the scenario where with 2 gates we can just distinguish those 2 types. But I'm not sure how to do that just using the classical gate. But apparently the quantum gate, they can do it just with 1 query gate. So from what I understanding, this is the big deal of the Deutsch algorithm. It really doesn't solve any other problem except this case, except for this very contrived, special, very simplified situation. That's all it does. But what it proves is for some problem, the quantum algorithm can be faster than classical computing algorithm. So that's basically what it just showed. In principle, the quantum algorithm can solve some problem faster than classical algorithm. That's the importance why this makes. It's in practice, from the practical sense, this really is probably never solve any practical problem. But ideally, it's important because it shows in some problems, quantum algorithm can be faster. So, and this is actually what my understanding. This is one of the first situations. Some people show for certain problem, quantum algorithm can be faster. So.
So is it about like the parity? Is it about like checking because I know that parity is used for like correctness, like if it is received correctly or not. So I'm trying to link that with like to understand it better. So is it about like to have this kind of, and that's why the quantum would be faster than that, so as to make this kind of checking or something?
Well, yes or no. I don't think a quantum computer for that. Maybe but let's say for the parity check for the in the computer system, I think many of those are also hardware implemented, if I understand correctly. So, well, at least some of them are hardware implemented. In this case, it's actually not just parity check. It's actually different. When you say the parity check in the data integrity, file integrity, that actually is work on the input. But for the Deutsch algorithm, we're actually not working on the actual parity check itself. We are trying to tell what is the function of this. We are not actually to see the parity output. It's actually trying to work on the function for that parity check. So, good question, but that's actually is the important point I'm trying to emphasize here. The Deutsch algorithm is actually not working on the parity check itself. It's working on this function. In fact, for the Deutsch algorithm, you can see the input. It is a 0, cat 0, cat 1. That actually is carefully designed. Yeah.
Not like the other one is random as mentioned before, or not?
You mean the classical one?
Uh-huh.
That part I'm not sure. Yeah, but for the Deutsch algorithm, in fact, this kind of one is carefully designed so that there will be so-called phase kickback. So, yeah.
Thanks.
So it is intentionally designed. Then the lower qubit here is cat one. So when apply these two Hadamard gate, and then they will generate a phase kickback. And what this does is going to have the undesired result canceled out, desired result are coming out. So that's so with this single gate, it basically cancel out the undesirable result, undesirable outcome. That's from my understanding, this kind of one is a very is carefully chosen for these purposes. There's actually the IBM tutorial actually go over all this mathematical way to show why this work. I'm hesitant to go over that directly because that seems to be a very that's quite a lot. But the IBM tutorial actually indeed go over this mathematical to show why this algorithm works. So what it does is actually do this step by step. So it first check the system status after the two Hadamard gate, and then check another status after this unitary function gate. And after that, it check the third one. And it actually does that step by step to show why this worked. It's really a lot. But the important part is it's trying to from what I got the gist is it basically put this f function using my understanding using the phase kickback, using the phase operation with the cat one carefully chosen, the undesired result will be canceled out. So, and this is also the advantage of quantum computing. Classical gate, it cannot do this. So with this, it's actually, with quantum computing, the f function goes to the phase, operate on the phase transition part, and it can get this done in one query. So yes. So it does have so it goes to with oh, my pen doesn't work on this anymore. So I can use my mouse to circle. So it does have this pi 1, cat pi 1 and cat pi 2. After the two Hadamard gate, it work on the pi 1. So that's the pi 1 situation. So cat 1, cat 0. By the way, notice it really doesn't matter the order as long as you know where that is. So cat 0 is here, cat 1 is the bottom one, but the bottom one is not leftmost. So the cat 0 is plus, cat 1 is minus, and there, that's the negative sign of the cat 1. And it's just expanding out. Oh, this is after the Hadamard gate, because Hadamard gate produced the superposition. So the cat 1 superposition, cat 0 minus cat 1. The cat 0 superposition is cat 0 plus cat 1. So that's the two terms expanding out. Am I making sense here? I'm trying to explain the
Yeah, I thought we're gonna make the tensor product for this 2H first, and then we're gonna make that, or I mean, like these two Hadamard gate, are they gonna be parallel and
this
then do the 0 1, or
very good. Pay attention here. This is the tensor product. Notice this 1/2. The Hadamard gate is 1/√2. So that is the product of two Hadamard gate.
yes?
Yeah. So I mean, it's missing one step. If we expand that to Hadamard gate, and we should get this one. Yeah. Yeah. So I think they should put the Hadamard gate here. I think this has a mistake. They should put the two Hadamard gate on the bottom at the front. Yeah. So this, I think there's a I think that's a mistake. You cannot write this one directly to that because there's a Hadamard gate missing here.
I think they're representing it with the like the matrix maybe, and this is the output directly.
Yeah. Good point. This pi1, cat pi 1, that's correct. But the intermediate part, that one should have the two Hadamard gate on them. And then expanding out. So this is a mistake. Good question. Yeah. So that actually really should put a two Hadamard gate there as a tensor product of the two initial one. Yeah. So then the result will be correct. So that's it, unless this plus minus is representing the bottom and up state. It really depends on the meaning of that two symbols. Yeah. So if it's a 0 and 1, oh, it didn't say 0 and 1. Maybe that's the reason. If it's a 0 and 1, it's definitely incorrect. But it says plus and one minus, so I'm not sure whether that two have a special meaning here. So yeah, the initial state is 1 and 0. That's right. And then it applied the two Hadamard gate become minus plus. I see. So it does intentionally, right? So this minus plus is after two Hadamard gate operation. So if I read the sentence above that, so the initial stage is the cat 1, cat 0, applying to Hadamard gate, and then the RBN tutorial called that cat minus, cat plus. Okay, so I guess that is correct. So basically, Hadamard gate is represented by the cat minus and cat plus. So I would still prefer to write it out to make it more explicit. So yeah. Yeah, so then expanding the two Hadamard gate on the cat 0, cat 1, cat 0, we have this. Yeah. So that's pi 1. And then after applying that unitary gate on the pi 1, so we got pi 2, cat pi 2. Cat pi 2, it basically expanding that on by applying a function. That function is applied from F0 or F1. F1 doesn't do anything. F1 doesn't do anything. and F0 yeah, this part of I'm going to assume this mathematically is correct. Apparently, it put the mathematically, if we apply that, that basically become the power, which is a phase operation. So let's just accept that is a mathematical phenomenon or rule we can use. So by applying this formula on the pi 2, we basically have this. So if it's a 0, there's a 1. That's basically become the pi 2, and then we apply the superposition again. We got pi 3. So finally, the actual proof that is, if it's even, it's 0. If it's constant or balanced, that's the result. Yeah, this is quite a lot. Some of this, especially the exponent short term, that part also new to me. But I would just assume mathematically people have approved. That's just correct. And so that part, yeah. So this basically in turns coming to this. So you can actually see F1 really doesn't matter here. So you can also see at the top, say, yes, we have a Hadamard gate. After superposition, apply the gate, and the bottom one doesn't matter anymore because after superposition, the unitary gate all goes back to the Q0 qubit. And then we just observe phase on a Q1. So the bottom one doesn't matter anymore. So basically we have just one output. If it's a classical gate, I guess this still have to continue, which explain why it needs at least more than one gate. But the quantum query gate, with this just one query gate, we can get the output there. So what's really important lesson here is called a phase kickback. And that's the one of the reasons why quantum computing is faster than solving some problem than classical computing method. So this phase kickback, or I guess intuitively we can call that a phase cancellation, is one way why quantum computing solve some problem faster than other classical ways. So we actually have the Qiskit implementation. Qiskit, so one confusing part when we apply the Qiskit is you realize we have to implement for F1, F2, F3, F4. This actually really confused me first, why we have to implement 4 different functions. And then I realized that is the input Deutsch algorithm work on. So why there are 4 implementation of that 4 function. Right, that's basically the 4 input we are working on. And F1, F4 should be balanced, constant. F2, F3 should be balanced. So I think we actually I have the code also on I have the code in the canvas. Let me see what so what I did basically copy paste the IBM code step by step into the Qskit and then run it in IBM Quantum Lab. So, well, let's go over that briefly before we run the code. So this is so you can see it does work on 1, 2, 3, 4 possible functions. And for each function, it's going to implement a different circuit. So with each function, the gate actually operates, have a different outcome. So this is function 3. So that's after function 3 is implemented, the quantum gate look like this. And this result will be balanced, yeah, because that's F3. So this result will be balanced. Yeah. So let me see whether in the let me go to Canvas, see whether I have this one. Yeah, so in the Canvas class side, I put my code there, Deutsch algorithm. Do you see that?
Yes.
Let me put that in the chat. Yeah. So I put that in the chat window. So unfortunately, it's hard to run this on the Colab. So you really need to run that in the IBM quantum environment. So if we go to the IBM Quantum Lab, oh, it is very slow. And maybe it's a good thing there's a lot of people are using IBM Quantum Lab now. So maybe that's also a positive sign. Yeah. Okay, so I think Hannity and some of you already use this. So I've often just use a Python 3 kernel. And actually, I already put my Deutsch algorithm somewhere here. Yeah. So you can actually see I did it up last week. So I did it for all the possible choices. 1, 2, 3, 4. Well, there are only 4 choices. So if I run the first part. So this is the tutorial example, number 3. Yes. And then I did then I draw the entire oh, by the way, so this might look different from the book because there's a OR gate, not just flip the bottom one into 1. So 0, 1, there's an extra OR gate just to flip the bottom qubit into 1. So then followed by Hadamard gate, that's where the pi 1, cat pi 1 is. And in the between, that will be the Deutsch, the unitary query gate for the Py function 3, followed by the Hadamard gate and readout. So, okay, I don't see the running readout coming out. But it didn't print out the running readout. It should print out the balanced. Okay, I missed the printout. It just draw the gate. Okay, and let me try just run everything, make sure it is that run everything? No, there's an error. Okay, let me try to run from start to the bottom. Let's run every cell, make sure it is there. At the bottom, I did have it print out. So 3, 2, yes, I did try for everyone. So here, so when we have the first one, it is constant. If we work on the second one, it's balanced. If we work on the third one, it is balanced. If we work on the fourth one, it's constant. So, and those actually show what's in the unitary gate after applying the Deutsch algorithm actually on the function itself. So it is when I work on this, it didn't occur to me why the unitary gate work on function giving me different circuit. So basically, if you look at the circuit, you see the in between the query gate also changed. That actually, I didn't understand the importance of that when I first read the code, but then I realized the algorithm is actually trying to work on the input, and that actually is supposed to change because the function itself is the input we are working on, not the actual Q0, Q1. Q0, Q1 is just there to help us find out what function are input. Okay. Yeah, I know even though I'm trying to go over this, but you probably need to work on this and try to appreciate this from your own experience. So I'm going to stop here and ask you, can some of you share your screen whether you can run the code in your IBM Quantum Lab? Justin, Joshua, Hannity. Hannity, you probably can do that. Can you share your screen, show other how you can run this?
Okay. I need to basically go to what is it called? The IBM Quantum.
Yeah, IBM Quantum Lab. Quantum first. The way I often do it, I'll go to IBM Quantum Experience. That one shows up on Google, and then from the IBM Quantum Experience, I select the link for the IBM Quantum Lab.
Yeah, I think I need to log in, right? That's
Yeah, you need to log in to run it. Yeah, so
okay.